Safety is the most important aspect of any electrical maintenance job. Everyone who works on or around electrical equipment must know what the dangers are and what steps can be taken to make sure that all personnel are protected from these dangers. Electricity is used to light control rooms and process areas, to power machinery and equipment, to control processes, and to do many other things. The flow of electrical energy is called current. Current flows through a wire similar to the way that water flows through a hose. A small stream of water can flow easily through a small hose, while larger flows require larger hoses. The same is true for electric current. A small amount of current can be carried by a thin wire, but a large amount of current requires a heavier wire. Current is measured in amperes, which are often called amps for short. The electrical pressure that causes current to flow is called voltage. Voltage is measured in units called volts. Voltage pushes current through a wire in the same way that water pressure pushes water through a hose. A wire that's connected to a voltage source is said to be energized or hot, but there must be enough voltage to overcome the wire's electrical resistance before current will flow. Resistance is the opposition that a material presents to the flow of current. It's measured in units called ohms. Current can pass easily through some materials, but not through others. This copper wire, for example, has low electrical resistance, so current flows through it easily. A material that current can flow through easily is called a conductor. Other materials, such as rubber, have high electrical resistance. Materials such as these are called insulators. Electrical shock is the body's physical reaction to a significant amount of current flow through it. The more current there is flowing through the body, the stronger and more dangerous the shock. And you can pretty well assume that the lighting and equipment circuits where you work carry more than enough current to produce a fatal shock. But even a relatively small amount of current flowing for a long enough period of time can seriously injure or even kill a shock victim. The longer the amount of time that the body has current flowing through it, the more severe the shock. The third shock severity factor we're going to look at is the path that the current takes through the body. It's important to note that current will only flow if there is a complete path for it to follow. For example, if a person touches an energized conductor with one hand and another part of the same circuit with another part of his body, the person becomes part of the circuit. In other words, a complete path for current flow is provided, and the person will receive a shock. The reason that the path current takes through a person's body can affect the severity of a shock is that some parts of the body are more vulnerable to the effects of current flow than others. For example, a relatively small amount of current flow through the heart is more dangerous than a larger amount of current flow that does not pass through the heart. In general, current will flow through all available paths, but most of the current will flow through the path of least resistance. Although the human body is a conductor of electricity, it does offer resistance to the flow of current through it. Different people have different amounts of resistance, and so do different parts of the same body. The amount of resistance that an individual body offers to the flow of current can vary from 1 minute to the next. At any time, a person's electrical resistance is affected by the person's physiology, emotional state, and the amount of moisture on the skin. The most frightening aspect of these effects is that even the most severe effects can be caused by current values that are much less than 1 amp. and electrical equipment is often capable of supplying hundreds or even thousands of amps. Sometimes people survive a shock by sheer luck, and sometimes they don't. Now's a good time for you to check your understanding of this material. Whenever you work around any equipment that is or may be energized, you need to be on the lookout for electrical hazards. For example, moving or working on ladders near energized components can be hazardous. If you're not careful when you're moving a ladder, it's easy to hit electrical equipment. In addition, just being on a ladder means that you're closer to circuits than you normally would be. Overloading a circuit by connecting too many devices to it can cause the wiring in the circuit to get hot. Under certain conditions, the wiring could get hot enough to start a fire. Not all electrical hazards are visible. One hazard that's not visible is associated with induced voltage. For example, even if one of the wires in this cable tray is not connected to a source of voltage, it can still become energized. Current flowing in a nearby energized wire creates a magnetic field that can induce a voltage and cause current to flow in the disconnected wire. Another type of electrical hazard is associated with backfeed. When backfeed occurs, a circuit is energized but not from its normal source. For example, a circuit could be set up to be fed from its normal source under normal conditions and from a battery under emergency conditions. Even if the circuit is disconnected from its normal source, it could still be energized from the battery. Standing water may not look dangerous, but it can be hazardous if energized electrical equipment comes into contact with it, or if you're standing in it while you're using energized equipment. Also, standing water can be a slip hazard. Lightning can also be an electrical hazard, but it's a hazard that can be minimized by the installation of lightning rods. The hazards we've just seen can be clearly identified as electrical hazards. However, electrical maintenance work involves more than just wires and energized equipment. So you have to be alert to some other types of hazards as well. For instance, working around batteries is a hazardous aspect of electrical maintenance work. The most obvious hazard that batteries present is a shock hazard. Coming into contact with the battery's terminals and connected parts can be very dangerous. Batteries also use chemicals that give off hydrogen gas as a byproduct. Hydrogen forms a hazardous mixture when it's combined with oxygen in the air. The slightest spark can cause an explosion. For this reason, smoking is not allowed in battery rooms. Proper ventilation is extremely important in battery areas. Vents reduce the chance of explosion by safely removing the hydrogen gas and also the acid vapors given off by batteries. The acid that batteries contain can burn human skin and many other materials. Because of the chance that battery acid may come into contact with someone's eyes or skin, the proper protective equipment should be worn. This equipment typically includes an apron, goggles, gloves, and a face shield. In case battery acid does come into contact with someone's eyes or skin, it's important to know where wash stations are located. Everyone who works in the area should know where the nearest wash station is and how to use it. Arcing is another common electrical hazard. An arc is an electrical spark that occurs when current jumps across an air gap, such as when contacts are opened. Strong arcs can burn or blind a person nearby. Arcs can be caused by a number of conditions. One common cause of arcs is pulling out one end of a fuse that's carrying current. To prevent an arc from forming when a fuse is pulled, the current flow through the fuse should be stopped first. This can be done by turning off the power to the fuse or by turning off the equipment that's connected to the fuse. If there's no current flowing, an arc cannot form. An important chemical hazard associated with electrical equipment involves polychlorinated biphenyls, or PCBs for short. For many years, PCBs were used in liquid insulation and as a coolant in some types of electrical equipment, such as transformers. Today, however, the use of PCBs is restricted because they are known environmental contaminants, and they have been linked to cancer and other health problems in humans. Protective equipment is necessary for anyone who might come into contact with PCBs. Always look for PCB warning labels on the equipment that you work on. If you're not sure, assume that you're working around PCBs and take the necessary precautions. Another chemical hazard associated with electrical maintenance involves the solvents that are used to clean equipment, such as motors. Many solvents are skin and eye irritants. Some can also be poisonous when they're ingested or absorbed through the skin. Solvents in spray or aerosol form can be dangerous in another way. Small aerosol particles or solvent vapors can mix with oxygen in the air to form a combustible mixture. There's one more important consideration to remember whenever solvents are used. Some solvents can chemically damage electrical insulation. This may result in injuries or equipment damage caused by short circuits, grounded circuits, and even fires. Whenever possible, it's best to use an approved solvent that is non-flammable and non-toxic. If you're unfamiliar with the solvent, be sure to check the solvent's Material Safety Data Sheet, or MSDS, and the solvent's container labels for important safety information. When potentially hazardous solvents are used, it's essential to have adequate ventilation to prevent combustible mixtures from forming in the work area. It's also important to wear the appropriate protective equipment. In some cases, a face shield and safety goggles are required to protect your eyes and face from sprays and splashes. You may also need to wear a respirator to protect your lungs. If your work involves soldering, you should know that working with a hot soldering iron can be dangerous for more reasons than just the possibility of getting burned. Soldering can produce hazardous fumes, so it should be done only in a well-ventilated area. This will help to minimize your chances of breathing in any of the fumes. Hot solder can spatter, so be sure to wear the proper eye protection. It's also a good practice to use a stand. A stand will keep the iron within easy reach, and it will also keep the hot iron from coming in contact with flammable materials. Now's a good time to check your understanding of job-related hazards by answering a question. You probably hear a lot of talk about safety. It's also likely that you see warning signs all around your facility. One thing that you should never do is take safety for granted. Many people think that accidents can never happen to them, that safety's for other people. But carelessness and improper shortcuts are two big causes of industrial accidents and injuries. Safety is especially important when you're working around electricity. You can't see electricity, but that doesn't mean that hazards aren't there. If you don't take precautions, electricity can be deadly. If an accident does happen and you're faced with an emergency, you should be prepared to respond quickly. To find out exactly what to do in a given set of circumstances, you should learn what's contained in your facility's emergency action plan. However, in this part, we're going to go over some general guidelines for two situations: aiding a shock victim and fighting an electrical fire. Everyone who works around electrical equipment should know how to help a victim of electrical shock. One of the first things that should be done is to report the situation. Another is to cut the power to the area if possible. If the power cannot be cut, you'll need to follow your company's specific procedures for what to do as an alternative. In some cases, it might be possible to use a non-conducting pole or rope to separate the victim from the electrical source. In any case, though, you should not touch the victim with any part of your body. If you touch the victim with any part of your body, you may get an electrical shock too. If you use a non-conducting pole or rope, you can move the victim without touching him. When you're sure that the victim is separated from possible shock sources, you need to determine the victim's condition. If the victim has stopped breathing, or if the victim's heart has stopped beating, you may need to administer CPR, or cardiopulmonary resuscitation. Everyone who works around electrical equipment should be trained in proper life-saving techniques. Another type of emergency situation that you may face is an electrical fire. Most facilities have special training requirements for fighting fires. You need to know and follow your company's specific guidelines at all times, but there are some general guidelines for firefighting. One of the first things that should be done is to cut power to the area of the fire if possible. Another thing that should be done is to report the fire. After these two actions are taken, an attempt may be made to put out the fire. If you need to use a portable fire extinguisher, make sure it's designed for putting out electrical fires, which are Class C fires. A fire extinguisher that's rated Class A, B, C can be used for almost all types of fires, including electrical fires. Three types of fire extinguishers that may be available are carbon dioxide fire extinguishers, dry chemical fire extinguishers, and halon fire extinguishers. Generally speaking, it's good practice to leave firefighting to the professionals. Trying to be a hero could get you killed. However, if you work around electricity, you should know how to use a fire extinguisher correctly, just in case. Now take some time to try a question on emergency actions. There are several types of basic protection available to personnel who work around electrical equipment. Some of the electrical equipment in your facility is accessible to many people. This equipment is designed to prevent exposure to its energized parts during normal operation. And the controls for the equipment should be used only by personnel who are assigned to operate the equipment. However, when maintenance is required, the equipment could be opened up, creating a potentially hazardous situation for people who are working on or near it. To inform workers of hazards in an area, warning tape and signs are commonly used. Locks and tags also warn personnel that equipment is not to be touched. In most cases, it's not enough just to warn personnel that a hazard exists. To prevent accidental exposure to the hazard, barriers are set up. In some situations, the barrier consists of warning tape around a work area. In other situations, hazardous equipment may be enclosed in an area surrounded by a fence or a wall. Access to the areas within barriers is usually restricted as indicated by locks, tags, or signs. In addition to helping prevent accidental exposure to hazards, locks and tags are also used to prevent control mechanisms from being operated by mistake. In other words, they provide a positive means of controlling hazardous energy sources. Now try a question about basic protection from hazards. One of the best ways to control hazards around energized circuits is to use approved insulating gear to provide protection from electrical shock. This insulating gear can include rubber gloves, rubber sleeves, and rubber blankets. And it's used in addition to the regular protective gear that's normally required for maintenance work. Rubber is used because it's an insulating material, and it provides a barrier between electric current and your body. When rubber gloves are worn to provide protection from electrical shock, separate leather covers are worn over the gloves. The leather protects the rubber from punctures and other types of damage. Rubber gloves with leather covers are essential protection for anyone who is working around energized circuits or circuits that could become energized. The rubber is the insulating barrier, and the leather protects the rubber. Both materials are necessary. Company procedures and safety manuals typically contain information on when to wear rubber gloves and what types of rubber gloves are required in specific situations. Rubber sleeves can be used along with gloves to provide additional protection. The combination of gloves and sleeves protects the hands, arms, and shoulders from electrical shock. Rubber blankets have several uses. For instance, they can be used to insulate workers from ground. If a worker who is standing on a rubber blanket accidentally makes contact with an energized circuit, the current cannot flow through his body to ground, so he will not get shocked. Rubber blankets can also be used to cover energized circuits and equipment while work is going on around them. They provide a protective insulated barrier for the workers. Since rubber protective equipment provides insulation from electrical shock, it's essential to inspect the equipment before using it. Rubber gloves should be checked carefully for cracks, worn spots, cuts, and holes. A simple and effective way to check for small punctures is to twirl the glove to trap air inside it, and then gently squeeze the glove to see if it stays inflated. This inspection is extremely important. Even a pinhole leak can be enough to allow current to enter your body. It's usually a little more difficult to thoroughly inspect rubber sleeves and blankets than rubber gloves because there's no easy way to inflate them. The best thing to do is to examine the rubber as carefully as possible to make sure that there are no obvious cuts or punctures. A good way to do this is to roll the material tightly, which stretches the rubber. Then carefully examine the rubber material where it is bending. That way, it's easier to detect any small cracks or holes that might otherwise be missed. In addition to on-the-job checks, many companies have procedures for thoroughly inspecting all insulating gear on a periodic basis. These procedures generally involve performing both visual inspections and electrical checks on the gear. While the procedures and schedules can vary from one facility to another, the purpose of all of them is the same: to make sure that the insulating gear will do its job when it's needed. The hazards associated with electrical maintenance can be controlled in several ways. One way is by following established procedures for making equipment safe to work on. One commonly used safety procedure is called lockout and tagout. It's used for controlling hazardous energy sources, including electrical energy sources. Lockout and tagout involve several things, including employee training and periodic verification by auditors and inspectors. In this part of the program, though, we're going to focus on aspects of lockout and tagout that electricians deal with as they perform maintenance activities. Keep in mind that your safety depends on knowing and following your company's procedures. An effective lockout and tagout procedure describes the steps that are necessary to make sure that equipment is shut down and isolated from energy sources such as electrical power. The procedure is designed to make sure that equipment is safe to work on. The term lockout refers to the use of locks or similar devices on deactivated equipment, such as electrical circuit breakers. The lock actively prevents the passage of energy from a source to the equipment being worked on. Tagout refers to the use of tags to warn people not to operate equipment. but the tags do not actively prevent the equipment from being operated. However, there are some situations where locks can't be used. For instance, some equipment, such as this on and off switch, can't be locked out. When equipment can't be locked out, tags are extremely important. To work properly, tags must be part of a comprehensive safety program. They must provide protection that is equal to locks in their ability to control energy, and they must be put on and removed by well-trained, qualified employees. A lockout and tagout procedure sets requirements on the types of locks and other energy isolating devices that can be used. For instance, all isolating devices, such as this chain that's used to hold a valve in the closed position, must be authorized for energy isolation. In addition, they must be capable of withstanding the environment they're used in. When locks are used, they must be substantial. That is, they must be strong enough so that they can't be opened without the key unless excessive force or unusual procedures are used. When tags are used, they should warn against hazardous conditions that can occur if the equipment is improperly re-energized. Tags must carry standard warning labels such as "Do not operate," "Do not close," or "Do not energize." Tags must be attached to the equipment with non-reusable self-locking devices that are capable of withstanding a force of 50 pounds. What we've seen about lockout and tagout so far basically involves one person. However, major repairs that require several groups of workers are sometimes performed. That's when a group lockout and tagout is needed. In many cases, a device such as this is used to allow each group to affix an individual lock or tag. A group lockout and tagout procedure should provide as much protection as an individual one. In addition, an authorized employee must account for all members of the group and make sure that everyone is protected through all shift and personnel changes. The authorized employee must apply a personal lock or tag to the group lockout device before work is started and remove the lock or tag when work is complete. By following the lockout and tagout procedures in place at your facility, you can help control hazards, and you can perform your work safely and efficiently. Now try a question on locking out and tagging equipment. Proper grounding is an important safety consideration for almost all electrical equipment. Proper grounding provides a low resistance path to ground for current that might otherwise go through someone's body. For example, this motor is properly grounded. The ground bus connects the motor's housing to a grounding grid that's buried in the earth. If the motor develops a fault, the normally de-energized housing could become energized. But through proper grounding, any current that's flowing in the housing because of a fault condition is directed to ground through the grounding strap and back to the motor's source of voltage instead of through a worker. Like equipment that's installed in your facility, proper grounding is also required for many portable tools that you may need to use. Any tool that has a metal casing should be equipped with a grounded three-pronged plug. When the tool is plugged into the proper type of receptacle, the third prong connects the tool's casing to the equipment grounding terminal in the power receptacle. This means that fault current will travel from the tool's casing to ground through the ground conductor in the power cord, not through the body of the person using the tool. If an electrical tool is double insulated, it does not have to have a ground conductor in its power cord. Double insulated tools have plastic casings that insulate the user from any fault inside the tool. If the casing is in good condition, there is little danger of shock. One word of caution is advisable, though. Not all plastic-coated tools are double insulated. Plastic casings are used for comfort as well as for insulation. Before you use any ungrounded plastic-coated tool, be sure to check the tool to make sure that it really is double insulated. Now's a good time to check your understanding of tool safety features. Because of the hazardous nature of the work, there's a big difference between being able to perform electrical maintenance work and being able to perform electrical maintenance work safely. Being able to identify electrical parts means knowing what various pieces of electrical equipment are, what they look like, and whether they are normally energized. For example, the equipment in this cabinet is used to provide power for plant lighting and other applications. To be able to work safely on any of these circuits, you need to know that it contains buses, connections, insulators, cables, cable supports, and a ground bus. You also need to know that during normal operation, the buses and their connections can carry large amounts of current, but the insulators, the cable insulation, the cable supports, and the ground bus do not normally carry current. Of course, just because a part is not normally energized does not mean that it cannot become energized. Being familiar with specific electrical components is an important part of working safely. Another aspect of performing electrical work safely is determining the nominal or normal operating voltage of a circuit or a piece of equipment. One way to get information about the nominal voltage for a circuit or a piece of equipment is from an electrical diagram. Another way is to read the information on the equipment's nameplate if one is available. Being able to determine the nominal voltage level of a circuit or a piece of equipment is an important part of working safely because it helps you determine the types of protective gear you'll need. Another aspect of performing electrical maintenance work safely is knowing minimum safe clearance distances. As part of the preparations for electrical maintenance work, temporary barriers should be set up to keep non-electricians at least 10 feet away from the work area. There are also minimum safe clearance distances for qualified electricians who are performing maintenance work. These distances are associated with the various voltage levels at which equipment can be energized. For example, let's say that this connection is energized at 480 volts. The minimum distance that a worker must keep between this component and himself, or anything that he's holding, is 1 foot. In this case, 1 foot is the minimum safe clearance distance. In this topic, we went over different ways of controlling the hazards that you face on the job, ways that include protective equipment, safety features incorporated into tool design, and procedures for ensuring safe working conditions. Now take some time to try a few practice questions. In many companies, insulating gear is sent to a central location for testing. Here, a technician is getting ready to test a group of gloves. Before the gloves are tested, they are washed with a mild soap to remove dirt or other conductive materials that might have accumulated on them. This is a test apparatus that's used to perform dielectric tests on insulating gear. The apparatus can test 6 gloves at a time. Each glove that's being tested is first filled with water and then lowered into a water-filled tank in the apparatus, which is connected to ground. A hot lead then applies the test voltage to the water inside the gloves. The technician monitors the test by watching a current meter to be sure the leakage current through the gloves remains within acceptable limits. For this demonstration, we stuck a pin partially through a glove before the test began. The pinhole is very difficult to see with the naked eye. Now watch what happens when the test voltage is applied. The test voltage burns through the area weakened by the pinhole and begins arcing to ground. This causes circuit breakers in the test equipment to open, de-energizing the apparatus, and aborting the test. If this glove had been used on a job, an accident could have occurred. Strong arcs can burn or blind a person nearby. Arcs can be caused by a number of conditions. One common cause of arcs is pulling out one end of a fuse that's carrying current. To prevent an arc from forming when a fuse is pulled, the current flow through the fuse should be stopped first. This can be done by turning off the power to the fuse or by turning off the equipment that's connected to the fuse. If there's no current flowing, an arc cannot form. In some cases, it might be possible to use a non-conducting pole or rope to separate the victim from the electrical source. In any case, though, you should not touch the victim with any part of your body. If you touch the victim with any part of your body, you may get an electrical shock too. If you use a non-conducting pole or rope, you can move the victim without touching him. Locks and tags are used to prevent control mechanisms from being operated by mistake. In other words, they provide a positive means of controlling hazardous energy sources. Being able to determine the nominal voltage level of a circuit or a piece of equipment is an important part of working safely because it helps you determine the types of protective gear you'll need.